Hello friends, today we will be continuing our discussion on the sterile products. We had looked into the aspects of what are the constituents of the sterile products. Today we will be looking into few more aspects of how the presence of pyrogens and what other tests need to be performed so that the main point of the formulation of sterile products, that is the sterility of the product, is maintained. So we will be looking now into the aspects of the principles and procedures of how sterility testing can be done using membrane filtration and direct inoculation methods. Also, what requirements are there for the personnel which are involved in the formulation of the sterile products and how they contribute towards aseptic processing. Also, the processes for equipment cleaning and sealing of bottles which are required for maintaining the sterility. Also, the quality control tests like leak test and clarity test will be discussed, and how aseptic processing and testing methods can be used to ensure integrity and safety of the sterile products. So, the people who are involved in the sterile product production are generally unprofessionals, non-trained professionals, and they need to be upgraded with respect to in what manner the sterile products need to be manufactured. So, to be effective operators, they must be inherently neat, orderly, reliable and alert, and have good manual dexterity. These employees should be in good health state and should be subjected to periodic physical examination. The attire worn by these personnel in the aseptic areas usually consists of sterile overcoats, hoods, face masks and shoe covers. Sterile rubbers based gloves are also required. Personnel entering the aseptic area should be required to follow a definite preparatory procedure like removing at least outside street clothing, scrubbing the hands and arms thoroughly with a disinfectant soap, and donning the prescribed uniform. The initial processing step in the formulation of the aseptic products is the procurement of the components. First and foremost of them, and usually used in most of the sterile products, are the water for injection. These are generally prepared by distillation in a still specifically designed to produce the high quality water which is required. Reverse osmosis is the method that is used and approved by USP. The specifications for a still should include feed water pre-treatment, that is using chemical softeners, deionization or filtration to enhance distillate quality and minimize boiler scaling. Vapor purification, this includes an efficient baffle system to remove entrained contaminants before condensation and expel volatile substances before condensation to prevent contaminating the final condensate. So, volatile ejection is the next step. So, the material for construction which is used for the construction of these stills are that they must be of non-leaching type. Pure tin, 304 stainless steel and borosilicate glass is generally used. Reverse osmosis is used, which applies a pressure of 200 to 400 psi to force water through a semi-permeable membrane, which is opposite to the natural osmosis. Membranes which are used are of cellulose esters or polyamide nylon types. The help in retaining macromolecules and more than 85% of small ions, effectively remove pyrogens, macromolecules and visible microorganisms. By passing the water through two membranes in series, this can give more efficiency. Then the storage and distribution of the water is also important. So, closed tank with filtered air exchange to prevent entry of microorganism, dirt and vapors during filling and emptying is important. Temperature must be maintained at 80 degrees centigrade using a steam coil at the bottom of the tank to inhibit the microbial growth. Also, the water for injection should not be held for more than 24 hours at room temperature before use. if stored at 80 degrees centigrade. Continuous addition of fresh water for injection during use is a common and acceptable practice. Now, cleaning of the equipments and containers is also a mandatory step. New unused containers and equipments are contaminated principally with dust, fibers and chemical films. Equipments used previously should be scrubbed by hand immediately after use with an effective detergent that does not leave a residue of its own. Wherever possible, the equipment should be disassembled so that each part can be thoroughly scrubbed and cleaned. A new method for large tank pipelines and associated equipments that can be isolated and contained within a process unit has been developed and is identified as clean in place system for cleaning of the equipments. The cleaning is mainly done using high pressure rinsing treatments. The cleaning is delivered automatically within the equipment. For small glasses or metal equipments, machine washing is suitable. Items are typically cleaned in an inverted position. Washing process includes a hot detergent rinse, hot tap water rinse and final rinse with the distilled water. Now, detergent treatment is usually eliminated for new glasswares to avoid detergent residue. Cleaning cycle becomes essentially a rinsing process. Use of alternating hot, preferably clean steam and cold water treatments is done to loosen the debris. Now, final rinses should be done with filtered water for injection. Rubber closures are cleaned by mechanical agitation in a tank of hot detergent solution, generally 0.5% sodium pyrophosphate, followed by a series of thorough water rinses with final rinsing by water for injection. The cleaning removes surface debris from molding and handling. Leachable constituents at or near the surface. Some debris is electrostatically attracted to the surface. Plastic materials also accumulate surface debris similarly. Cleaning aims to remove the debris, along with it loosen the debris, minimize abrasion and sweep away loosened particles. Autoclaving may be included as a part of the cleaning cycle. The product should be compounded under clean environmental conditions. In large batches, it is crucial to achieve and maintain homogeneity of the solution, suspensions and mixtures. Maintenance of the required temperature is important. Accelerated cooling is also required when needed. Filtration of solutions is essential for clarification and sterilization. The main difference between clarification and sterilization is the degree of filtration. Clarification, also called polishing, removes particles more than or equal to 3 micrometer. Sterilization basically removes particles down to 0.3 micrometer, including viable microorganisms and spores. The highly polished solution appears exceptionally pure and clear. It reflects high quality, especially important for the sterile solutions. The basic machine features for filling containers with liquids must deliver measured volume with efficiency. So, a mechanism to repetitively force a measured volume of liquid through a delivery tube. Then the delivery tube design is important. Size is determined by the container opening, liquid viscosity and density and desired delivery speed. The tube should easily enter the container neck and be deep enough to allow air escape without disturbing the liquid inside. To reduce resistance, the tube diameter should be maximized. For small volume delivery, a plunger stroke of a syringe is used. The stroke of syringe forces the liquid through a two-way valve that provides for an alternate filling of the syringe from a reservoir and delivery to the container. These parts also should be constructed of non-reactive materials such as borosilicate glass or stainless steel. Vacuum filling method is also used in high speed filling lines for large liquid volumes, highly suitable for automated production systems. The working principle of a vacuum filling method is that a vacuum is generated inside the bottle when a nozzle gasket seal against the bottle lip. The vacuum draws liquid from a reservoir into the bottle through the delivery tube. Levels must be controlled and the filling must stop after it has reached the required level. So, to take care of this, filling continues until liquid reaches the adjustable overflow tube. At that point, the seal is mechanically loosened, the vacuum is released, stopping the flow of the liquid. Now, filling equipments for solids. So, sterile solids like antibiotics harder to subdivide into accurate doses compared to liquids. So, the flow rate of solids is irregular and slow, especially when finely powdered. Small granular particles flow more evenly than the fine powders. So, the containers also used for the sterile solids must have relatively higher openings for efficient filling. The machine filling of free flowing solids must be used if the solid is relatively free flowing. These involve volume based measurement calibrated to desired weight. The common problems in machine filling are the stratification of particles due to size variation, electrostatic charge buildup within the solid mass, air pocket formation, clumping, which leads to uneven flow and filling. Solutions which help in minimizing these issues are one is optimization of the particle size and its distribution, applying a small electric current to neutralize electrostatic charges. Auger based filling machines are used, wherein an auger in the stem of a funnel shaped hopper is used. Auger size and rotation speed can be adjusted. This delivers a regulated volume of material into the containers. Sealing. Containers should be sealed immediately in the aseptic area right next to the filling machine. Sealing helps in retaining the sterility of the product, hence tamper proof sealing is essential. Now, ampule sealing methods which are used for sealing of ampules is generally by melting the glass neck in an aseptic environment. There are two common types of seal. One is a tip seal, which is formed by melting the tip of the ampule neck to create a glass bead. Then there is a pull seal made by heating the ampule neck while rotating, pulling the tip away to form a narrow capillary and sealing it by melting. A high temperature gas oxygen flame is used for melting. Heating must be uniform to avoid deforming of the seal. Overheating can cause expansion of air or gases, leading to fragile glass bubbles. Improper sealing, that is open capillaries or cracks, can cause leaks and compromise the sterility. Now, the rubber closures are also used. So, the must fit container opening snugly to ensure a seal, but not too tightly to hinder the placement. A common manual method used is vacuum assisted tool to pick and place closures into vials. For machine insertion, closures are often halogenated or silicone coated to reduce surface friction. This allows smooth movement from a rotating or vibrating drum down a chute. Closures are then inserted into containers by a plunger or similar pressure device. High speed production line stopping is achievable with this system. Aluminium caps are used to hold rubber closures in place. Single caps may have a permanent center hole or a center that is torn away at the time of use to expose the rubber closure. Double aluminium caps usually have an inner cap with a permanent center hole, which in use is exposed when the center outer cap is torn off. The triple aluminium caps are used for larger bottles with rubber closures having permanent holes for attachment to administration sites. The inner cap with a permanent center hole remains in place during use to secure the rubber closure. The thin disc is used in conjunction with a thin rubber disc to seal the holes through the closure. The outer cap holds the disc in place and is torn away at the time of use. So, the sterilization of a product, that is generally for a freeze dried product, follows these set of process. First is the preparation, that is aseptically formulating as an aqueous solution or suspension, then freezing to sub-zero temperatures, then sealing the chamber once the product is fully frozen, then evacuation, applying vacuum to initiate sublimation. Upon sublimation, that is, ice transitions directly to vapor and is captured in a refrigerated condenser. The resulting cake, which is the dried residue, retains original volume, forms a porous structure for easy reconstitution. So, from preparation to the cake, formation occurs in the bottle. The rate of drying depends largely on the thermal conductance of the frozen product, rate at which the vapor can diffuse through the progressively thicker layers of the dried porous material, and the rate of transfer of the vapor through the system to the condenser surface. Here is the freeze drying process summarized point wise. So, automatic control, heat input control, moisture reduction, moisture protection, and in chamber stopping occurs. The drying rate, approximately 1 hour is needed for each millimeter of product depth. Applications: freeze drying is used to preserve biological preparations, tissue sections, and viable microorganisms. Multiple vitamin combinations, antibiotics, and hormone preparations are generally preserved by freeze drying. Packaging is also important, and this helps in maintaining the quality, purity, and reliability of the product. The packaging must be dignified, neat, and attractive to inspire user confidence. Single dose injection containers must not exceed 1 liter to avoid reuse and contamination as per USP. The 3 general areas of quality control are: first is the incoming stock, manufacturing, processing, and then the finished product. So, at these three areas or the 3 points, the quality of the material needs to be controlled. For the sterile products, incoming stock control encompasses routine tests on all the ingredients as well as special evaluations such as pyrogen test on the water for injection, glass tests on container, and identity tests on rubber closures. The microbial load test is performed to determine the number and types of microbes bioburden present. The process control involves monitoring various parameters during manufacturing such as conductivity during water for injection distillation, volume of fill in containers. So, the important aspects of packaging have been mentioned here. Sterilization, cycle time and temperature, label count, and identity verification. Product control includes final tests and assays before product release. The sterile product tests are done to ensure the stability of the product. So, they must undergo leak test, clarity test, pyrogen test, and sterility test. The leak test is intended to detect incompletely sealed ampoules so that they may be discarded. Tip sealed ampoules are more likely to be incompletely sealed than those that have been pull sealed. In addition, small cracks may occur around the seal or at the base of the ampoule as a result of improper handling. So, negative pressure is created in a vacuum chamber with ampoules submerged in the methylene blue dye with the percentage of 0.5 to 1%. Upon vacuum release after 30 minutes at a pressure of 27 inches of mercury, the dye enters any leak and becomes visible after washing. An alternative method can also be used by immersing ampoules in a dye bath of red colored 1, red color 2 and sodium lauryl sulfate during autoclaving, which helps in improving the leak detection, and it also sterilizes simultaneously. The detection limitation is that capillaries less than or equal to 15 micrometer may escape detection by standard methods. Vials and bottles, no leak test due to flexible rubber closures is there, often sealed under vacuum to maintain negative pressure throughout shelf life. The vacuum detection in bottles is done by water hammer test. Striking the base produces a distinctive sound. Spark test, a blue spark occurs when a probe moves from the liquid to airspace if vacuum is present. Clarity, it is subjective and varies by observer. Visible particles in the range of 30 to 40 micrometer or larger are hard to eliminate completely. So the USP requirement is that visual inspection is mandatory. Every unit must be visibly inspected for the particles. As per USP, the particle limits for large volume infusions is maximum 50 particles more than 10 or equal to 10 micrometer per ml are permitted, and 5 particles greater than or equal to 25 micrometers per ml are permitted. Suspensions, emulsions, dry solids and solutions must be compounded and processed under clean conditions to reduce foreign particles. The visual inspection could be done by manual process. Each container closure system is inspected individually under good lighting against a white and black background. Contents are swirled to make particles easier to detect. Care is taken to avoid detecting the particles or confusing the particles in place of air bubbles. So, containers may be inverted to spot heavy particles. The human efficiency can be affected by fatigue, eye strain and distractions. This can be applied to 100% of the products with accuracy comparable to the end users. Obviously, it is dependent on the person who is doing it, so it is an advantage. However, instruments can also be used like light scattering, light absorption, electrical resistance for determining the particle count and size distribution. Destructive testing can also be done. So, most methods require destruction of the product, which is a loss. So, this is generally not preferred, but wherever required and indispensable, it is also used. Non-destructive imaging. Video images are taken of the product to identify the moving particles. This is limited to 1 to 5 ml containers only. Pyrogen testing in parenterals is done, and it is determined by qualitative biological tests based on fever response in rabbits. Rabbits are ideal because their response is similar to the humans. If a pyrogenic substance is injected into a rabbit's vein, temperature elevation occurs within 3 hours. The LAL test, that is stimulus amoebocyte lysate test, is done. So, the reagents are prepared. The LAL reagent is reconstituted using buffer under aseptic endotoxin free conditions. Serial dilutions of endotoxin standard are created for preparation of a standard curve. Negative control using endotoxin free water is also kept in place. Positive product control by spiking the sample with a known amount of endotoxin is included. Test samples should be free from substances that inhibit or enhance LAL reaction. The samples must be diluted if there is interference. Now, 0.1 ml of the test sample is added into a depyrogenated test tube. Then 0.1 ml of reconstituted LAL reagent is added to the same tube, gently mixed without creating bubbles. It is incubated at 37 degrees for 60 minutes. After incubation, tubes are removed and inverted to 180 degrees gently. Formation of a firm gel that remains intact upon inversion is a positive result, indicating the presence. A negative result, that is no gel formation or a gel that collapses when inverted, is indicates towards the absence of the endotoxins. For detecting the presence of viable form of microbes, membrane filtration method or direct inoculation method is used, which are basically sterility testing methods. In the membrane filtration method, which is generally used for filtrable aqueous preparations, alcoholic or oily preparations, and preparations miscible with aqueous or oily solvents, this is performed under aseptic conditions with strict precautions against contamination. The media must support the growth of aerobic, anaerobic microbes and fungi. Fluid thioglycolate medium is primarily used for anaerobic bacteria, but also supports aerobic bacteria. This is used for clear fluid products. Alternative thioglycolate medium is used when products are turbid and viscous. In this fluid, there is absence of agar and resazurin. The soybean casein digest medium is used for fungi and aerobic bacteria. So, the next is the process for the membrane filtration. Equipment and filter setup requires use of closed reservoir plus receptacle with a 0.45 micron membrane. The filter is selected based on the solution type, that is cellulose nitrate is used for aqueous, oily, weak alcoholic solutions. Cellulose acetate is used for strongly alcoholic solutions, and there are special filters for antibiotics. The membrane is rinsed with sterile fluid for aqueous soluble solids. It is rinsed with sterile fluid, that is peptic digest. For oily ointment or water oil emulsions, the membrane is rinsed with fluid D. In case of antimicrobial properties is there, it is to be rinsed 3 to 5 times with a sterile diluent. So, for the sample filtration, the product is transferred to the membrane unit. Dilute viscous or oily products with suitable diluent, that is isopropyl myristate is used. For the aerosol product, they are frozen at -20 degrees in alcohol and dry ice and then added to fluid D. Then pre-filled syringes without needle, it is expelled into membrane funnels or pooling vessels. However, with the sterile needles present, direct expulsion into the membrane unit is done. After filtration, the membrane is aseptically cut into 2 halves. One is transferred into fluid thioglycolate medium and incubated at 32.5 degrees centigrade, and the second half is incubated in soybean casein digest medium, incubated at 22.5 degrees centigrade. Incubation in both the media should be for at least 14 days, and the growth pattern of the microbes has to be done. Indication of growth shows contamination of the product. So, this is the product quality for sterile testing of the various kinds of products like the liquids, antibiotic solutions, insoluble preparations, creams, solids and medical devices. The sample size which is generally used for sterility testing has been mentioned in table 3. Now, for direct inoculation, the preparatory method step involves transferring prescribed quantity of the product into the culture medium directly. It is to be ensured that the product volume should be less than 10% of the medium volume. Medium is the media which will support the growth. So, for oily liquids, creams and ointments, dilution must be done with fluid D in the ratio of 1:10. Sterile devices must be immersed intact into the medium. Surgical dressings, aseptically, the inner portions must be removed and immersed. Catheters can be cut into pieces to expose lumen, or the lumen may be filled with the medium. In case of large volume, concentrated preparation must be used and directly added into the media. Then it must be incubated for at least 14 days. Minimal shaking is done if thioglycolate medium is used to maintain anaerobic conditions. If the medium becomes turbid after 14 days, then more than or equal to 1 ml portions are transferred into fresh medium and incubated. Both both the original and new vessels must again be incubated for more than 4 days additionally, extra 4 days, and then they must be compared for and analyzed for the growth of microbes, and a call must be taken about the sterility of the product. So, this is the procedure for direct inoculation. Thus, to conclude, the sterile products are critical in ensuring product safety, especially in parenteral therapies. Strict aseptic techniques and clean room practices are essential to prevent microbial contamination. Material selection and handling significantly impact product integrity. The preparation and testing of sterile products demand strict adherence to aseptic protocols to ensure patient safety. From personal practices to equipment cleaning, sealing techniques and sterility testing by membrane filtration or direct inoculation, each step is critical. Moreover, quality control measures like leak tests and clarity assessment further guarantee product sterility. A deep understanding of these procedures ensure the consistent production of high quality contamination free sterile pharmaceutical products. So, I hope you would have a fair idea of what sterile products are like, what is expected from the people, the facility, as well as from the testing point of view, so as to make a product sterile. Thank you very much for your patient hearing. Have a good day. Thank you.